Hello, grade 10s. In our last lesson, we took a look at what the numbers meant around a chemical symbol. We learned about subscripts and coefficients and how to count atoms. Today, I want to look at chemical equations. I want to look at those sentences that tell us what's happening when I mix chemicals. And I want to look at how we can balance them. When we talk about the sentence that talks about what happens in a chemical reaction, we often talk about the reactants, which is the left-hand side, and the products, which is the right-hand side. The reactant side tells us what we're mixing, the things that are reacting. In this example, hydrogen is reacting with water. The plus sign is not like a plus sign in math. It just means reacts with. The arrow separates the reactants from the products. It tells us a chemical reaction now happens, and we are going to produce something, and the right-hand side now is our products. We are producing water. This can be done as word equations, but can also be done as a skeleton where we use chemical symbols. Hydrogen and oxygen are both diatomic. We remember this from our lesson on covalent compounds. They react to produce water. The symbol for it is H2O. This is called a skeleton because, well, this does happen. It does not happen in these ratios. It does not tell me how much hydrogen and how much oxygen I need in order to produce water. In order to do that, I need coefficients. Coefficients are the large numbers that go in front of each species in a chemical reaction. They tell us how many groups we need. I know that I'm going to need 2 groups of hydrogen atoms reacting with 1 group of oxygen atoms to produce 2 groups of water molecules. When we don't see a number in a balanced equation, we assume it to be the number 1. We will need 1 of them. You'll also sometimes see symbols in brackets around your equation. Those symbols tell us about the physical state that they may have reacted in. S means solid, L means liquid, G means gas. Sometimes you'll see the symbol AQ because some substances need to be dissolved in water before they react. So while these little symbols that we have in the brackets are helpful to us to let us know what physical state was required to make this reaction happen, they themselves do not have any effect on the balancing, and we do not try to balance these symbols. What does balancing mean? Well, balancing comes from something called the law about conservation of mass. When we have a chemical reaction happening, what we basically have happening is a rearrangement of the atoms. If we think about the reverse reaction of the one I was talking about earlier, water breaking down back to hydrogen and oxygen. Written as a skeleton, you'll notice that this is not the same. When we take a look at the before side, I see 1 oxygen and I see 2 hydrogens. In the after side, I have 2 hydrogens, so that's the same, but it looks like I have 2 oxygens. At this point, it looks like an oxygen just magically appeared. This side of the equation would be heavier. There are more of it. It would weigh more. That's how we know it is not balanced. When we put the coefficients in front of each species, you can now see that when 2 water molecules react, there are 2 red oxygens, and we have 1, 2, 3, 4 yellow oxygens. This matches the reactant side that has 1, 2, 3, 4 hydrogens and 2 oxygens. So this is now a balanced equation. This is balanced because we see that we have 2 oxygens before and 4 hydrogens, and on the after side of the arrow, on the product side, again there are 2 oxygens and 4 hydrogens. When the amounts are the same before and after, this is considered to be balanced. Let's check if this reaction is balanced. We start by making a quick inventory to see what kind of atoms are involved. I can see that we have hydrogen atoms, we have chlorine atoms, and we have magnesium atoms. This should be the same on both sides. We should have hydrogen atoms, chlorine atoms, and magnesium atoms. Counting the amounts that we have, I see 1 hydrogen, 1 chlorine, and 1 magnesium. After the reaction, 1 magnesium, 2 chlorines, and 2 hydrogens. While the magnesiums match, the hydrogens and the chlorines do not. This reaction is not balanced. So how do we go about balancing a reaction? How do we go about fixing this scenario? We're going to need to first check, like we just did, to see if we have the same amounts. But then we need to add those coefficients, the big numbers that go in front. We know that we're going to need to have more than one group of some of them. So let's go through a list of rules to help us figure out how to find out how many groups we will need. Start by getting the unbalanced equation, and I recommend that you draw boxes around each species, all the formulas. It's a really important thing because it reminds us that we never ever change anything inside the boxes. The boxes are there to remind us that those formulas represent specific chemicals, and if you change them, you have different chemicals. So those little subscripts that are beside each chemical have to stay there. Then we make the chemical inventory. We'll figure out how many we actually have. We won't know if we're balanced until we check. Finally, we will use the coefficients. Coefficients talk about how many groups. And again, if you remember from the last lesson on counting atoms, coefficients refer to multiplying. We're going to go through the couple of examples together. All right, we're going to break this down into the individual steps. Let's start with the unbalanced equation. In this reaction, we're going to react sodium hydroxide and hydrogen sulfate. They're going to react to produce sodium sulfate and water. We're going to make sure that we separate these by drawing boxes around each of the formulas. My formulas are always separated by plus signs or arrows. Remember that the reactant side is everything on the left, the product side is everything on the right. In this case, there are 2 reactants and 2 products. In this case, we have several different elements, but I am going to put my boxes around the entire species because that helps to remind me that I can't change any of the numbers or the letters inside the boxes. Now we need to make a chemical inventory. We need to make a list. I can see that before the reaction there are sodium atoms, oxygen atoms, hydrogen atoms, and sulfur atoms. We separate before from after by an arrow. Before being everything on the left and after being everything on the right. Counting before the reaction, we'll see 1 sodium. I will see 1 oxygen here plus 4 more there is a total of 5 oxygens. It's okay that they're in separate squares. I just want to know how many in total there are. I count that there is 1 hydrogen here and 2 more is 3 hydrogens, and there is 1 sulfur. On the after side of the arrow, there are 2 sodiums. There is 1 sulfur. There is 4 oxygens and 1 more is 5 oxygens, and there are 2 hydrogens. Checking to see what matches. Sodiums are not the same, oxygens are good, hydrogens are not the same, and sulfurs are good. So this reaction is unbalanced. Not everything is the same. So we're going to look for things that we can change to make them the same, and the factor that we're looking for is multiply. This one and this one needs to be fixed. And changing 1 sodium into 2 sodiums is the first easy place to go. I can see that by multiplying the amount of sodiums by 2. I had 1, and by putting a 2 in front of it, multiplying it by 2, I end up with 2 sodiums. So what I had to do was find sodium on the before side and put a 2 in front of it. Now sodium balances. This too, however, affected everything inside the box. It did change the sodium, but it also changed the oxygens. I now have two groups of 1 is 2, plus these 4 is 6. My oxygens don't balance. It also affected the hydrogens. I had two groups of 1 is 2, plus these 2 is 4 hydrogens. My hydrogens don't balance. And my sulfurs were unchanged. So it might seem as though we're no closer, but in reality we are. Let's try fixing another case. The 6 to 5 on the oxygen isn't immediately apparent, but changing the hydrogens is. I can easily change a 2 into a 4 by multiplying by 2. So what I need to do is find hydrogens on the after side. Here they are, and multiply them by 2. I do this by putting a coefficient. Putting the coefficient in front of this hydrogen now changes 2 times 2 is 4 hydrogens, which now balances. It also changed the oxygens. I now have 2 oxygens here, plus 4 more is 6. That balances. From before, our sodiums are still balanced and our sulfurs are still balanced. This reaction is now considered balanced. What do we do when we have a case where I've got 2 of something on one side and 3 of the other? When there's no 1 multiplier? Well, you always can factor it and find the lowest common multiple. I could make them both into 6. Let's do a few more examples together, and we'll go through some where that might be a condition. In your notes, you'll find this example. I've already put the squares around each species for you and made the element inventory. Let's start by counting to see how many we have before the arrow and after the arrow. Remember, my before and after side is separated by the arrow. Before the reaction, no number after the sodium means there's 1 sodium. Looking for sodium after the reaction, again, there's no number, so there's 1 sodium. The sodiums look good. Before the reaction, no number after the chlorine means there's 1 of them. The number after the chlorine here is 2, so that one's not balanced. Before the reaction berylliums, I have 1. After the reaction berylliums, I have 1. Looking good there. For fluorines, we have 2 of them before the arrow and only 1 after. So that's not balanced. My chlorines and my fluorines are not balanced. What multiplier can I use? Well, 2 chlorines here and 1 there, I could multiply by 2 to make them balance. Multiplying chlorine by 2 on the before side means find chlorine before the arrow and put a 2 in front of it. Now I have 2 chlorines. I fixed the chlorine problem. But you notice inside the square is also sodiums. So my sodiums are now being multiplied by 2. My sodiums no longer balance. To make it work, on the after side, I'd have to multiply sodiums by 2. So finding sodium on the after side and putting a 2 in front of it fixes the sodium issue. This meant 2 sodiums. It also meant 2 fluorines. So I put a 2 here. Now my fluorines balance. This equation is now balanced. What do we do with the blanks that don't have a number in them? In these cases, you can substitute the number 1. Again, we don't have to write 1s in chemistry, but in balancing reactions, quite often you will have people fill in the blanks with a 1 because it works as a placeholder. Let's try the second example. First, counting to find out how many of each we have. No number after the iron means I have 1 iron. The 3 after the chlorine means I have 3 chlorines. The 3 after the beryllium means 3 berylliums. My P's and my O's in my phosphate group are in brackets. The little 2 means I have 2 groups of them. So 2 groups of P's is 2 P's. 2 groups of 4 oxygens is 8 oxygens. After the arrow, we start with beryllium. No number after the beryllium means I have 1. 2 after the chlorine means I have 2 chlorines. No number after the iron means 1 iron. No number after the phosphorus means 1 phosphorus. And after the O, we have a 4. My irons look good. Chlorines don't balance, berylliums, phosphoruses, and oxygens. We have a lot of work to do. As mentioned earlier, we have this even-odd number problem with the chlorines. There's no one number I can multiply them both by, but I do know I can make them both into a 6. If I multiply chlorine before by 2 and after by 3, then I'll have 6 chlorines before and 6 after. To multiply by 2, that means I have to go to the before side, find chlorines, which are here, and multiply them by 2. I put a big 2. To get the chlorines after the arrow multiplied by 3, I find chlorines after the arrow and put the big 3. Now, there's other things in these brackets. This has made 6 chlorines, 2 groups of 3, but it also made 2 irons. So the irons before the arrow are now at a 2. This did make 3 groups of 2 with 6 chlorines, but it also changed the berylliums. I now have 3 of the berylliums. So my chlorines are good, my berylliums are good, but I've now messed up the scenario with the irons. We can fix that though. I know that if I multiply irons after by 2, that would make them equal. Finding iron in the after side of the arrow, I put a 2 in front of it. My irons now match. This 2 meant 2 times iron. It also changed the phosphoruses to a 2, and 2 groups of 4 changed the oxygens to an 8. Checking again, the oxygens and the phosphoruses now balance. This reaction is now balanced, and I can substitute a 1 in this empty blank as a placeholder. There are 2 more reactions to balance here. This would be a great place for you to pause the video. Try them on your own, get as far as you can, and when you're ready, press play again, and we'll see how you did. Press pause now. All right, let's see how you did. In this first example, I've already drawn the squares for you and started the inventory. Let's take a look at the counting and see what happens before the reaction on the left-hand side of the arrow and after the reaction on the right-hand side of the arrow. Before the reaction, I can see we have 1 silver, 1 nitrogen, 3 oxygens here and 1 more there is 4. It doesn't matter that they're split apart, we just need the total number. There's 1 lithium and 1 hydrogen. After the arrow, I count 1 silver, 1 O and 3 more is 4, 1 hydrogen, 1 lithium, and 1 nitrogen. My silvers match, nitrogens, oxygens, lithiums, and hydrogens. Everything matches. There's nothing more to do. We can fill in each blank with a 1 because as written, this is a balanced reaction. Let's try the one below. Starting by drawing a square around each species so that I remind myself not to change anything inside the square. I can see that I have carbons, hydrogens, and oxygens. Before the reaction, there's 1 carbon. After the reaction, 1 carbon. Before the reaction, 4 hydrogens. After, 2. Before, 2 oxygens. After, 2 here and 1 more is 3. The carbons look good. The hydrogens and the oxygens do not. I can fix the hydrogen problem by multiplying by 2. 2 times 2 would be 4. I need 4 hydrogens on the after side. On the after side, hydrogens inside this square, so I'm going to multiply by 2. This has fixed the hydrogen. 2 groups of 2 is 4. It is now 2 O's plus these 2 is 4. My oxygens still don't balance. I can fix this by multiplying oxygens on the before side by 2. Looking for oxygens on the before side, I'm putting a 2 in the multiplier spot as a coefficient. I now have 4 oxygens. This equation is now balanced. Any blank left over can be filled in with the number 1. One more example. In this final example, we have a reaction that has magnesiums, manganese, and oxygen. Before the reaction, I see 1 magnesium, 2 manganeses, and 3 oxygens. After the reaction, 1 magnesium, 1 manganese, and 1 oxygen. A little clue that I can give you to help you with balancing is anytime you see elements listed by themselves, like the magnesiums or the manganeses, leave the balancing of them to the end, because you can really put any number you want in front of those without messing everybody up. Because I can leave them to the end, I'm going to balance my oxygens first. If I multiply oxygens on the after side by 3, I'll have 3 before and 3 after. That means look for oxygens on the after side of the arrow and multiply by 3. Now, this has changed the oxygens, but also the magnesiums. This is also now a 3. Fixing the magnesium problem, multiply this side by 3, the before side. Magnesiums are now balanced. All that I have left now to balance is manganese. I need to multiply the after side by 2, so find manganese on the after side and put a 2. Remember, any blank left over, you can put the number 1. We need to practice with balancing reactions. At the end of your workbook, you have several practice problems for balancing equations. I will also post another video below this in the comments to help you find more videos to help you understand and practice balancing equations.